In this video I will show how to use the MC33816 Analyzer tool, and as an example I will analyze the demo program provided by Freescale, and also I want the analyzer to plot the jump condition and the instruction in the blocks when it will plot some control flow graphs. So now I start the analysis, and we can see that the control flow graph is correctly reconstructed with 37 user-defined labels, 50 code blocks, and 80 links between the code blocks. The first check performed is the consistency checks, which checks for the jump and the wait instruction, and it checks that since these instructions depends on the correctness of the information contained in some registers in case of the jump instructions, or the wait table for the wait instruction. It checks that for every possible path that can lead to a jump instruction or a wait instructions, this register or wait table are correctly set. Then the main control flow graph is splitted into the interrupt service routine graph, and here we have the first warning, that is the two interrupt service routine, one for automatic diagnosis and one for a software interrupt, share the same exit point. This can be seen better if we plot the interrupt service routine, for example on a PDF file. For example, we plot a file called isr.pdf, and here we can see that effectively the two interrupt service routines share the exit point through a code block called restore, but they don't share the entry point. And the danger is that the code executed in the entry point, which is basically some initialization code for the interrupt handling, the danger is that this code can be missing in one interrupt service routine or the other, and here the solution would be to have a single entry point and then at runtime decide which interrupt has occurred. After generating the interrupt service routine graph, also the two subgraphs for the two microcores are generated. Then the infinite loop checks is executed on the three subgraphs that are generated. In the interrupt service routine graph, there are 4 cycles, and all 4 cycles are possibly infinite, while in the two main programs for the two microcores there are 21 cycles, of which there are 5 possible infinite cycles in the first microcore and only 1 for the second one. So we can see how these infinite cycles are composed and decide if these cycles are desired or if they are caused by an error. In the case of the interrupt service routine, there are 4 cycles, and all 4 have basically the same structure. That is, they keep the load driver in a blocked state, waiting for the main microcontroller to reset a flag as a signal that the load driver can continue its operation. And this occurs for all the four cases, and this is the expected behavior since this is an error handling. For the first microcore, the first cycle is an idle cycle where the two inputs start 3 and start 4 are not active, and in this case the output is also kept disabled. The second cycle instead is a cycle where the output is activated and is kept active by during a period which depends on the output current and two timers. And after this period has passed, if the input is still active, then this cycle is re-entered and the output is activated again. So this is a dangerous condition because it depends on a fixed level on the input. It would be better if it depended on a continuous check of the correctness of operation of the microcontroller. The same applies for the third cycle, where simply the input that is checked is the second input. And then we have two cycles which are sustained by a condition that is composed of the input signals and a special signal that is a combination of the input signals. So this cycle can be dangerous because it is composed of the boost block, which actually activates the output, and if this cycle is sustained, the output will be indefinitely active. So this must be broken, and in order to ensure that this loop never happens, it is important to correctly configure the special input, which is composed of a combination of all the start inputs. The same applies with the last cycle, where simply apart from the special input, it is considered the second input. Now, going back to the cycles corresponding to a normal activation of the output, we can save a graph of the whole program with this cycle highlighted in order to analyze it better. So, as said before, this cycle continuously activates and deactivates the output. It first passes through an idle block where the input condition is checked, and then the boost phase is reached where the output is actually activated. Then it waits for the output current to reach a predefined threshold, and then it waits for a predefined amount of time to pass during the peak phase, and then it goes to the bypass phase where it waits for another specified amount of time. Then it goes back to the hold phase, which is sustained by another timer. After this last timer has expired, it goes back to the idle code block after disabling the output. Now, a possible modification would be to insert an explicit check in between the input check and the output activation. That is, we could insert a check that ensures that the main microcontroller is alive. If the main microcontroller is alive, then the load driver can activate its output. I have modified the original boost block, which originally simply jumped from the input check to the output activation, introducing a code block called check boost, which checks a flag on the controller register to be continuously set by the microcontroller. If this flag is not continuously set by the microcontroller, the execution path goes to the end of injections phase, where the output is kept disabled. If on the contrary, this flag is set by the microcontroller for every cycle where the actuation is desired, then the execution goes to the boost code block where the output is activated. Now I can execute the analyzer on this new file. And we can see that there are still 5 possibly infinite cycles in the program for the first microcore, but in this case the first cycle is given by the condition of having one input active and not having this control flag enabled. This is the case, for example, where the microcontroller does not want the actuation to occur, but still has the input signal set, which shall never occur. But if it occurs, for example, because the main microcontroller is in fault, this will never activate the output. So the programmable load driver will stay in a safe situation. The second cycle is the same idle cycle found with the original program, and corresponds to both the input deactivated. And the third one corresponds to the case where the input is active. The main microcontroller sets the flag on the control register in order to enable the actuation, but in this case the output current condition is never reached. This can be given by a faulty actuator or some other error condition for which the threshold current is never reached. So in this case, a timeout makes the program go back to the idle phase, deactivating its output. The fourth cycle is a variation of the previous one for the second input, and the last cycle is a variation of the first cycle, where the second input is activated, but the microcontroller has not given its OK in enabling the output.